Section: Introduction. In this section, we will discuss the importance of pre-training large language models on vast amounts of unlabeled text. These models have shown great potential. However, aligning them to follow user instructions is crucial for practical use. Techniques like supervised fine-tuning have been less effective compared to methods that incorporate feedback to guide models towards more helpful responses. Despite the benefits of using feedback, these approaches are challenging to implement widely. For instance, the Proximal Policy Optimization (PPO) variant of reinforcement learning from human feedback (RLHF) involves a complex pipeline with 4 large language models interacting during training. This alignment process poses new challenges for efficient training, requiring a re-evaluation of various software aspects like model scalability and coordination among models. There are existing tools like Hugging Face TRL, Carper AI TRLX, and Microsoft DeepSpeed Chat for model alignment. However, with NeMo-Aligner, we aim to enhance the performance and scalability of methods like PPO, especially for very large models such as Llama 270B and beyond. NeMo-Aligner tackles scalability issues by leveraging Megatron LM with 3D parallelism training, a distributed approach to PPO training in RLHF, and integrating PPO inference optimizations based on Tensor RTL-LM during the rollout stage. These optimizations enable efficient training of the largest models across hundreds of GPUs, reducing research iteration time. NeMo-Aligner optimizes popular alignment techniques like supervised fine-tuning, SFT, PPO-based RLHF, direct preference optimization, SR-LM, and self-play fine-tuning. We will briefly explain these techniques in the following sections and provide a detailed exploration of training with each of them. Finally, we will showcase the flexible design of NeMo-Aligner. Now, let's delve into the background of model alignment techniques. Supervised fine-tuning involves updating a pre-trained model's parameters based on expected responses to prompts. This is crucial for reinforcement learning from human feedback and direct preference optimization to ensure the model generates responses aligned with user instructions. Reinforcement learning from human feedback eliminates manually defined reward functions by training a reward model from human preferences data. PPO is a common method in RLHF, focusing on training a policy with rewards from the trained reward model. Section Summary. In this section, we introduce the concept of training large language models, LLMs, using feedback to align them with user instructions for practical applications. While supervised fine-tuning, SFT, updates base models based on expected responses, reinforcement learning from human feedback, RLHF, trains a reward model from human preferences to guide the RL algorithm, with a focus on proximal policy optimization, PPO. NeMo-Aligner aims to enhance PPO and other alignment techniques by optimizing training scalability and performance, especially for the largest models like Llama 270B, through parallelism training and inference optimizations. Section: Direct Preference Optimization. In this section, we present Direct Preference Optimization, DPO, Self-Play Fine-Tuning, SPIN, and RLHF, PPO, training. In DPO, we use preference data to train an optimal policy directly without needing an explicit reward model. Instead of a reward model, we use a reference policy to calculate the reward difference between a chosen and rejected pair using the Bradley-Terry model. The difference in log probabilities between the chosen and rejected responses is scaled, transformed by the sigmoid function, and used to derive the loss. The reference policy remains fixed during training and is the policy used to generate the chosen, rejected responses. If the reference policy is not available, it can be approximated by supervised fine-tuning on the prompts and preferred responses. SPIN is a self-play algorithm where a strong model is developed by playing against previous versions of itself. New responses are generated from previous iterations of the model, and the policy is improved by distinguishing between these self-generated responses and the ground truth human-generated responses. The training process involves updating the model weights based on preference tuples of chosen and rejected responses. NeMo-Aligner supports various alignment techniques efficiently at large scales by incorporating features from Megatron LM and NeMo. The training pipeline includes stages such as supervised fine-tuning, reward model training, and proximal policy optimization. The challenges mainly arise during the proximal policy optimization stage, and our approach to addressing these challenges involves a distributed approach to PPO training. During PPO training, we run training and inference on 4 different models: PPO actor, reference policy, PPO critic, and reward model. To handle the large sizes of these models, we use a distributed approach with PyTriton servers to communicate across the models. By optimizing the communication and allocation of resources, we ensure efficient training of the models. Section Summary. In this section, we introduce 3 key algorithms: direct preference optimization, DPO, SR-LM, and self-play fine-tuning, SPIN. DPO uses preference data to train an optimal policy without relying on a reward model, while SR-LM focuses on supervised fine-tuning to align models based on semantic aspects of responses. SPIN is a self-play algorithm where a strong model is developed by playing against previous versions of itself, improving its policy through discriminating between self-generated and human-generated responses. Section: Optimizations for PPO rollout. In this section, we optimize the PPO rollout process. Response generation during the rollout was identified as the main bottleneck in PPO training. The actor's generation stage involves multiple forward passes, generating 1 token per pass. This process is memory bandwidth bound, so reusing the training stage implementation leads to poor performance. To tackle this issue, we used TensorRT-LLM, a high-performance deployment framework, for the generation stage. TensorRT-LLM optimizes inference kernels and fuses them into a TensorRT-based runtime for better performance. At the beginning of RLHF, the model is passed to TensorRT-LLM, which compiles it into a TensorRT engine. This engine contains model weights, while the runtime allocates memory for KV cache and activations. Before and after generation, the engine and runtime are loaded and offloaded respectively. Since generation requires less memory than training, we reshaped the model to use tensor parallelism only. During subsequent training steps, the engine needs to sync with updated parameter weights. To avoid recompiling the engine, we update it in place using TensorRT refit. We also noticed varying generation times among data parallel workers due to different response lengths. To address this, we set up a worker pool to balance the workload dynamically, giving shorter generation workers more tasks. Moving on to model training details and quality, we conducted large-scale RLHF training with NeMo-Aligner. We performed SFT on a Llama 270B model and trained a Llama 213B reward model using the Anthropic Hydrogen Hydride RLHF dataset. We then used PPO with specific parameters for each iteration. The model was trained for 100 rollout steps, achieving a performance of 7.59 on MT-Bench, surpassing the performance of the Llama 270B chat model. For scalability evaluation, we repeated training setups with different numbers of actor and critic nodes. The overall time per step decreased as we increased the nodes, showing speed improvements in both training and rollout stages. The scaling efficiency of NeMo-Aligner was evident in achieving speedups with increased node counts. However, the scaling of the training stage was sublinear due to the decreasing number of micro-batches per data parallel rank as the node count increased. In conclusion, our system demonstrated effective optimization for both training and rollout stages, showcasing scalability and performance improvements with increased node counts. Section Summary. In this section, we optimize the PPO rollout by addressing the bottleneck in response generation during training. We implement the generation stage using TensorRT-LLM to improve performance by leveraging optimized kernels and automatic kernel fusion. Additionally, we demonstrate the scalability of NeMo-Aligner by repeating training setups with varying numbers of actor and critic nodes, showing speedups in both the train and rollout stages as the number of nodes increases. Section: What contributes to system performance? In this section, we explored what contributes to the performance of our system. We conducted experiments where we removed different components of NeMo-Aligner's PPO system one by one to see how it affected the overall processing time per sample. We found that the integration of Tensor RT-LLM is crucial for high system performance. Without it, the processing time per sample would increase significantly. Following that, using Tensor RT refit, asynchronous requests between actor and critic models, and load balancing data parallel workers also played important roles in improving performance. For DPO training, we followed a specific training recipe using SFT and DPO on different datasets. We adjusted learning rates, batch sizes, and training durations to optimize the models. Our final models showed slight improvements in MT bench scores compared to previous models. We also explored Steer-LM training with LoRa, which allowed us to fine-tune large language models more efficiently. By applying LoRa to our training process, we were able to achieve a significant speedup while maintaining model performance. Additionally, we investigated spin training as an alternative to SFT, making some modifications to the training process. This approach yielded promising results in terms of model performance. Lastly, we designed NeMo-Aligner with extensibility in mind, enabling users to easily modify algorithms despite the complexities of distributed training. This flexibility allowed us to integrate various optimization techniques and model alignment strategies into our framework, further enhancing its capabilities.